Welcome to Cambridge IGCSE Physics, Lesson 17.1, Thermal Expansion of Solids, Liquids and Gases. Today we explore how materials change size when heated, a fundamental principle affecting everything from bridges to thermometers. This core content lesson builds essential understanding for your physics studies and practical applications in engineering and technology. Let's examine our learning objectives for today. By the end of this lesson, you will be able to: first, describe qualitatively thermal expansion of solids. This means explaining how and why solid materials increase in size when heated. Second, describe qualitatively thermal expansion of liquids and gases, understanding how fluids behave differently from solids when temperature changes. Third, understand expansion occurs at constant pressure, recognizing this important condition. These objectives align with Cambridge assessment objectives. AO1 tests your scientific knowledge, AO2 examines application skills, and AO3 covers experimental understanding. Now let's define our key vocabulary. Each term is essential for understanding this lesson. First, thermal expansion means the increase in size of materials when they are heated. This occurs because particles move more vigorously at higher temperatures. Second, qualitative means descriptive, rather than numerical analysis. We describe what happens rather than calculate exact amounts. Third, constant pressure means the pressure remains unchanged during the expansion process. This is important because expansion behavior depends on whether pressure or volume is held constant. Understanding these terms precisely is crucial for exam success and practical applications. Let's explore thermal expansion of solids. The fundamental principle states that solids expand when heated due to increased particle vibration. This means when we heat a solid, the particles inside vibrate more vigorously. As they vibrate more, the average separation between particles increases, causing the entire solid to expand. The expansion is typically small, but measurable and important. Key features include particles vibrate more at higher temperatures, average separation increases, and expansion is small but significant. Real examples include railway tracks which have expansion gaps, bridge joints that allow movement, and overhead cables that sag more in summer. The diagram illustrates this clearly. The cold solid shows particles close together, while the hot solid shows the same particles with greater separation, resulting in overall expansion. Now we examine thermal expansion of liquids. Liquid behavior differs significantly from solids. Liquids expand more than solids when heated because their particles are more mobile. Key differences include: first, greater expansion than solids, typically 10 times more expansion for the same temperature change. Second, particles are more mobile than in solids, allowing easier movement and greater volume changes. Third, expansion occurs at constant pressure, which is the normal condition for most liquid applications. Common applications include liquid thermometers, where mercury or alcohol expansion indicates temperature, and car cooling systems, where expansion tanks accommodate coolant volume changes. The diagram shows a liquid thermometer. Notice how the liquid level rises significantly when heated, demonstrating the substantial expansion of liquids compared to the solid glass container. Gas thermal expansion shows the most dramatic effects. Gas behavior demonstrates the greatest thermal expansion of all three states of matter. Key characteristics include: first, particles move freely with high kinetic energy. Gas particles are not bound together and move independently. Second, expansion is much greater than liquids or solids. Gases can double their volume with moderate heating. Third, volume increases significantly with temperature. This relationship is predictable and measurable. Fourth, gases follow specific gas laws when pressure remains constant. The important condition is that expansion is measured at constant pressure. This means the gas can expand freely without pressure changes. Real examples include hot air balloons that rise because heated air expands and becomes less dense, weather balloons that expand as they rise to lower pressure altitudes, and car tires that increase pressure when heated due to gas expansion in a fixed volume. Let's work through our first example. The problem asks us to describe what happens to a steel bridge on a hot day. This tests qualitative understanding of solid thermal expansion. Our analysis follows 4 steps. First, steel expands when heated. The bridge material follows the principle we learned. Second, bridge length increases slightly. Even small temperature changes cause measurable expansion over long distances. Third, expansion joints accommodate movement. Engineers design gaps that allow expansion without damage. Fourth, this prevents structural damage. Without expansion joints, the bridge could buckle or crack. The conclusion is that thermal expansion requires engineering solutions. The diagram shows a bridge structure with an expansion joint in the centre, allowing the bridge sections to expand safely when heated. Notice the support pillars remain fixed while the bridge deck can move. Example 2 explains how liquid thermometers work. The problem asks us to explain the operating principle of liquid thermometers. The principle is that liquid expansion indicates temperature changes. This is a direct application of thermal expansion. The operation involves 4 steps. First, liquid expands when heated, following the thermal expansion principle for liquids. Second, volume increases in the narrow tube. The expanded liquid has nowhere to go except up the thin tube. Third, height change shows temperature. The liquid level directly indicates the temperature. Fourth, the scale is calibrated for readings. Markings correspond to specific temperatures. The diagram shows a thermometer with liquid at 2 different temperatures. At 20 degrees Celsius, the liquid reaches one level. At 40 degrees Celsius, the liquid expands and rises significantly higher. The scale markings allow precise temperature readings. Now practice what you've learned with these 3 questions. Question 1 is basic level. It asks you to state what happens to particles in a solid when heated. This tests your understanding of the particle model and thermal expansion mechanism. Question 2 is intermediate level. It asks you to explain why liquids expand more than solids. This requires comparing particle behaviour in different states. Question 3 is advanced level. It asks you to describe how thermal expansion affects gas behaviour in balloons. This tests application of gas expansion principles. For all questions, remember to use scientific vocabulary correctly, explain particle behaviour clearly, and give relevant examples. Write your answers now before looking at the solutions. Think about particle movement, energy changes, and practical applications. Physics principles power our modern world. Let's see how thermal expansion applies in practice. In engineering, expansion joints in bridges and buildings prevent structural damage by allowing controlled movement during temperature changes. Engineers must calculate expansion amounts and design appropriate gaps. In technology, bimetallic strips use differential expansion of 2 metals to create thermostats and automatic switches. When heated, different expansion rates cause bending that triggers switching. In transport, railway tracks have expansion gaps to prevent buckling, and aircraft fuel systems account for fuel expansion at different altitudes and temperatures. These applications show why understanding thermal expansion matters for safety and functionality. Career-wise, this knowledge leads to mechanical engineering, aerospace engineering, and construction management. Essential skills include problem solving, design thinking, and safety analysis. Let's review the solutions. For question 1, the answer is: particles vibrate more vigorously when heated. The average separation between particles increases, and the solid expands as a result. This shows understanding of the particle model. For question 2, liquid particles are more mobile than solid particles, allowing greater movement and expansion when heated. This explains why liquids expand more than solids. For question 3, gas particles gain kinetic energy when heated. Volume increases significantly at constant pressure, so the balloon expands, or pressure increases if volume is fixed. Now for exam success tips. First, use the particle model. Always explain expansion using particle behaviour and energy. Second, compare states. Highlight key differences between solids, liquids, and gases. Third, give examples. Support your explanations with real-world applications. Fourth, understand command words. Describe needs features and observations, while explain needs reasons and mechanisms. Let's summarise today's lesson. The key points to remember are: first, solids expand due to increased particle vibration. Heating makes particles vibrate more, increasing average separation and causing expansion. This principle explains expansion joints in bridges and buildings. Second, liquids expand more than solids because particles are more mobile. liquid particles can move more freely, allowing greater volume changes for the same temperature increase. This explains how liquid thermometers work. Third, gases show the greatest expansion because particles move freely. Gas particles are not bound together, so heating causes dramatic volume increases. This explains hot air balloons and weather balloon behaviour. For further study, review the particle model of matter to understand why different states behave differently. Practice describing expansion qualitatively using scientific vocabulary. The next lesson covers heat transfer methods, which builds on today's work by explaining how thermal energy moves between objects and causes the temperature changes that lead to expansion.